Hey everyone, this is another video that was originally meant for my fellow classmates. However, once again, this information therein may be useful to a wider audience, and so I'm making this video available here publicly in the STEM at Play channel. You may hear me talk about you or us, in which case of course I'm speaking to my classmates. I may also reference our textbook, but you don't really need that specific textbook to be able to follow along in this video. So welcome, join us for the ride, and I hope that you find the information here helpful. Hey everyone, this is Jay, and welcome to Nutrition Basics. In this video, we're going to cover some of the very basics, the foundations, of our upcoming class section on nutrition. As some, maybe most, of you have figured out by now, the way that I best learn a subject is by first grasping its ideas at a fundamental level, by learning about it from the ground up. And I've noticed that some of you are like that as well, or at least it's helpful to you to start at the basics. So this video is for you guys. It should be noted that this video is not comprehensive, meaning that it won't cover everything in the book, or even everything in the first few chapters. There's no way we can do that in a quote-quote short video, so be sure to read up and study hard. This video is just a supplement, the building blocks to help you understand what it is you're reading. Well, we're going to talk about our nutrients, which the book defines as a chemical substance that is present in food and needed by the body. It then goes on to place nutrients into 6 major categories: saccharides, fats, proteins, vitamins, minerals, and phytochemicals. Wait, what? Okay, so right off the bat, you probably have a question or two. Let's address them before we move on. This last box here, phytochemicals? Isn't that supposed to be water or something? Well, depending upon which book you've read, sometimes the 6th nutrient category is water. And if you think about it, technically, water is indeed a chemical substance that is present in food and needed by the body. But not all nutritionists, and not all books, agree that it should be considered the 6th nutrient. If you've taken the CNA class here at FAS, for example, that may be why you think water should be in this box. But lots of other books don't even have a 6th box, and they just assume that water is an obvious need. Okay then, in that case, what the heck is this phytochemicals thing all about? Well, even fewer books define a 6th nutrient category to include phytochemicals, and it just so happens that our textbook happens to be one of them. The reason phytochemicals aren't widely accepted yet is that there's still a lot of research going on to determine whether they should really be considered a category of nutrient. In fact, our textbook may define them as a 6th nutrient category, but it barely talks about them itself, with only half a page of text with only 3 examples. We'll talk about phytochemicals in more detail later. The second big question you may have is with this first box, saccharides. Shouldn't that box read carbohydrates? Aren't saccharides just sugars? Yes and no. And when I say yes and no, I mean that literally. Yes, the box should, or more accurately, could be written as carbohydrates, and no, saccharides are not just sugars, even though it comes from the Greek word for sugar. Since this is the first box, let's go ahead and start talking about this category in detail. The word saccharide is another name for carbohydrate. Literally, they are synonyms, and you can use one or the other and still be absolutely correct, to a chemist, or an organic chemist, or a biochemist, or a nutritionist, or to any scientist, or to any doctor, really. Sadly, if you talk to your average Joe that way, then they may become confused, so feel free to just use carbohydrates, or carbs, when talking about nutrition to your clients. The textbook doesn't even use the word saccharide. It's not like the book doesn't know or is using it wrong, it just doesn't use the word at all, suggesting that they were well aware of the confusion it may cause, and they just wanted to avoid it. But I'm mentioning this here specifically because knowing this actually helps to understand how the whole category fits together. You see, carbohydrates can be further subdivided into 4 groups: monosaccharides, disaccharides, oligosaccharides, and polysaccharides. And technically, the main difference between them all is just, well, how big they are. Monosaccharides are your simple sugars, which means that they are made of a single sugar, hence monosaccharide. The textbook says that there are 2 of them, glucose and fructose, but there's actually more. Ever hear of ribose? That's another monosaccharide. But we don't need ribose for nutrition, you say? Okay, fine. How about galactose? That's yet another monosaccharide, and we don't absolutely need it, but we do metabolize it if we eat or drink it, unless you have galactosemia. And our bodies actually create it, for example, when mothers lactate. Disaccharides are exactly what they sound like, 2 monosaccharides linked together. The most common examples are sucrose, or table sugar, which is simply a glucose linked with a fructose, lactose, or milk sugar, a galactose linked with a glucose, and maltose, or malt sugar, which are 2 glucose linked together. Polysaccharides are a whole lot of monosaccharides linked together. The textbook says 10 or more of them, but the exact cutoff actually varies by convention. A common example is amylose, a polysaccharide which is just a ton of glucose bonded together in a chain, usually from 300 to 3,000 of them, and which makes up about 20 to 30% of the structure of starch. The other 70 to 80% of starch's structure, it's made up of amylopectin, which is another polysaccharide, made up of a crap ton of glucose monosaccharides, except this time it's not just in a single chain, but it's highly branched, and usually made up of 2,000 to 200,000 glucose subunits. Starch, by the way, is also a saccharide, specifically a polysaccharide, because it's made up of these two polysaccharides which, as we said, are each made of linked monosaccharides. Glycogen is another example of a polysaccharide that you should be familiar with. It's our body's storage form of glucose, and it's actually a glycogenin protein surrounded by a ton of glucose subunits. And finally, oligosaccharides, which are kinda in the middle. They're made of a medium number of monosaccharides, usually 3 to 10, but again, it depends on old conventions. Oligosaccharides may seem kinda like an exception, but they're actually super important. For example, they form parts of glycoproteins and glycolipids that make up antigens that, if you recall, allow our bodies to recognize which of our cells are what, so that we don't go all autoimmune on ourselves. Glycolipids are also key in determining our blood types. So, going back to where we started, monosaccharides are saccharides, disaccharides are saccharides, oligosaccharides and polysaccharides are all saccharides. In other words, polysaccharide doesn't mean a bunch of saccharides. It means one saccharide made up of a bunch of parts. They're all saccharides because they're all carbohydrates, so be sure not to get confused. Finally, let's talk about the one real kinda exception, fiber. Fiber comes in two varieties, soluble fiber and insoluble or dietary fiber. Cellulose is a well-known insoluble fiber. Some books will add them to the saccharides box because, technically, they are in fact polysaccharides. But some will place them like this, extending the saccharides box to place them outside of the nutrient category. This is because fibers, especially the non-soluble kind, are almost completely indigestible, and so calling them a nutrient largely depends upon your definition of the word. However, while they are not digested or absorbed and they are largely just passing right through us, they are important as roughage and bulking agents for your digestive tract. Well, okay, our body still uses fiber, so why bother making the distinction with nutrients about whether or not they're absorbed and metabolized by our body? Because the table of nutrients may also be grouped like this. These top three nutrients are known as macronutrients, and also as caloric nutrients. This means that they provide the fuel that our metabolic system needs to function, fuel that is converted to energy. These down here are called micronutrients, meaning they provide the cofactors for metabolism to be carried out, and not the energy or fuel itself. And on the average, saccharides provide 4 big C calories per gram of energy, which, by the way, a big C calorie is equal to 1,000 small c calories, or 1 kilocalorie. Because our textbook likes to use the term kilocalorie, or kcalorie, with a small c, then that's what I'll be using from now on. Just always remember that when people talk about how many calories their food has, or about how many calories they want to lose through exercise, they mean the big C calories. And so anyway, that's why many biochemists and nutritionists don't like to put cellulose and other fibers inside of the saccharides box. We don't metabolize them, and so they don't provide calories. And so each gram of fiber gives us 0 kilocalories of energy, not 4 kilocalories like the nutritional saccharides do. Now let's talk about fats, another of the caloric nutrient categories. These are basically all the different types of fats that you've heard about. These include your saturated fats, monounsaturated and polyunsaturated fats, essential fatty acids, trans fatty acids, hydrogenated and partially hydrogenated fats. Frankly speaking, this can be a very complicated category that can even be made into its own separate video because it would take quite some time to properly discuss them all. Here are the basics that are covered by the textbook, and thus the fundamentals that you need to know. Fats are the most energy-dense of the macronutrients, providing a whopping 9 kilocalories per gram of fat, more than twice that of saccharides and proteins. They usually come in the form of triglycerides, and it's in this form that they usually circulate through the bloodstream. Oils are actually fats that are liquid at normal temperatures. We need fats in our diets to be nutritionally complete, but as you've probably heard, some fats are certainly better for you than others. Placed in a rough order, essential fatty acids and other unsaturated fats are the good ones, and in fact, some we absolutely need. Saturated fats are the not-so-good ones, but unfortunately many of our foods have much more of them than we want, often even more than that's typically healthy. And the ones to try and avoid are the hydrogenated and trans fats. With that said, all fats, just like every other substance, can be unhealthy if too much is consumed. And wow, I feel like I just spent way too little time on a very complex subject. I may go ahead and make an entirely separate video going into detail about all these different kinds of fats and exactly why and how they may be good or bad for you, or maybe even make a presentation in class. But not here, or this video can easily break the 1 hour mark. One other detail that the book mentions, though, is the link between fats and cholesterol. Cholesterol is actually a sterol, which is a lipid, which is the category that fats belong to. So we can actually extend our diagram like this to include other lipids such as sterols, phospholipids, and waxes. Clearly these other substances are non-caloric, and in fact, some I wouldn't recommend eating. But the amount of certain fats that end up in your bloodstream have been correlated with the amount of cholesterol and also of other substances known as lipoproteins. And all of these in turn have been linked to cardiovascular disease, especially with high amounts of fats that were on the bad side of the list that we showed earlier. The textbook will go into lots more detail on this in Chapter 7, but for now, just know that this link exists. One more thing that the book mentions, although not in much detail because it was published in 2010, is that dietary intake of fats and cholesterol is not quite as bad for you as people thought. They're not the super terrible killer carcinogens and heart attack provokers that people believed them to be all throughout the late 20th century. I mean, yeah, consuming too much of either is definitely bad, but recent research, especially from 2013 through 2017, shows that consumed fats and cholesterol don't affect serum fat and cholesterol levels nearly as much as we thought. And we've known for a long time that there are actually some fats, namely the omega fatty acids, that actually help us to keep serum cholesterol levels in check. The key point, as always, is moderation. Keep an eye on the USDA recommended amounts, which is probably way less than most of you end up eating, and feel free to cut down on the bacon a bit. Just don't stress about it. The bad news is that other research since around 2014 has actually shown that carbohydrates may be more unhealthy for you than we originally thought. More research needs to be done in this field, but it turns out that all those turn of the millennium recommendations to cut down on fats and eat more carbs, they may have been a bit backwards. Of course, this doesn't mean that you need to stop eating bread and pasta right now, but let's say it one more time. Moderation. Don't eat too much of either fats or carbs, or especially simple sugars. Pay attention to the USDA's recommended amounts, and you and your clients will do just fine. Now let's talk about proteins. Proteins are made from amino acids, typically a whole lot of them. The protein hemoglobin, for example, which you may recognize as a protein found in erythrocytes that assists with oxygen transport among other things, consists of 574 amino acids in 4 distinct polypeptide chains. The largest known protein, titin, which is important in striated muscle contraction, contains from 27,000 to 33,000 amino acids in 244 individually folded protein domains. All proteins in the human body are made up of just these 21 different amino acids, and they combine to form all of the thousands of different proteins. How many? Well, as of 2015, we've identified over 18,000 of them. Depending upon whom you ask, we can expect to eventually identify anywhere from 100,000 to several million of them. The key to proteins and nutrition is the fact that they're made up of just 21 amino acids. When we consume proteins, we don't ever use them as is. Our body breaks them down into their amino acids, and then our body combines those amino acids into exactly the proteins that it needs. The huge advantage here is that we don't need to make sure we eat millions of different types of proteins. We just need to make sure we eat the right proteins to provide us with the 9 different types of amino acids. Wait, 9? Didn't you just say there were 21? Well, the amino acids used by us humans may be divided into 3 categories: essential, non-essential, and conditionally essential. We need all 21 of these amino acids, but our body does not create the 9 essential amino acids on its own. We must acquire them through our diet. We say that a consumed protein is a complete protein when it provides all 9 essential amino acids, while an incomplete protein has some essential amino acids, but not others. Generally speaking, animal protein sources contain many complete proteins, but most plant sources contain incomplete proteins. This is largely why, even though all living things, including plants, have proteins, those people with a vegetarian, or especially a vegan diet, may still not be consuming all of the essential amino acids that they need. It is important that vegans eat a wide variety of plant protein sources, so that the amino acids lacking from one may be supplied by another. There are a few plant sources with complete proteins, though, including quinoa, buckwheat, and soy, and one very simple combination, rice and beans, is also an excellent protein source when put together. The conditionally essential amino acids are the ones that our body can normally create except under certain limiting conditions. For example, preterm newborn infants or people in severe catabolic distress may have trouble synthesizing these. Thus, they must acquire these from external sources, such as their diet or supplements. The textbook has like 6 pages of details on most of the different amino acids, but I'll spare you by not making you sit there and listen to me read it all out loud. But be sure to read up on it yourself, just in case it's on the next exam. One little note, however, the book lists cysteine as a non-essential amino acid, and this isn't exactly correct. Cysteine is actually a non-proteinogenic oxidized dimer form of cysteine, which means it's an amino acid, and it is important for all the reasons the book says, but it doesn't actually form any proteins. The 21st amino acid that the book is missing is actually called selenocysteine, which is itself a kind of an oddball, but that again is more detail than we can reasonably cover in this video. Oh yeah, and proteins provide about 4 kilocalories per gram on the average. Okay, time to talk about vitamins. The book doesn't provide a solid, concise definition, but one commonly accepted definition of a vitamin is an organic compound and a vital nutrient that an organism needs in limited amounts because it cannot synthesize sufficient quantities on its own. Already you can tell that it's a rather vague definition, considering it can include almost every single substance that we've talked about so far, and in fact it's merely by convention that vitamins just don't include any of the other essential nutrients, such as essential fatty acids, essential amino acids, or dietary minerals. As of 2017, there are 13 universally recognized vitamins, which may be divided into 2 categories: fat-soluble vitamins, which are vitamins A, D, E, and K, and water-soluble vitamins, which are the 8 B-complex vitamins and vitamin C. The book also mentions choline, which is an essential nutrient that behaves similarly to vitamins, but isn't considered a vitamin because its importance and need isn't yet well understood. For this reason, an RDA, a recommended daily allowance, has not yet been established, although an AI, adequate intake, has been defined: 425 milligrams per day for women and 550 milligrams per day for men. As you can imagine, with 13 total vitamins, going through each and every one of them in detail is a bit too much for a quote-quote short video, so again I'll refer you to the textbook. But here are some general information that'll start you off with a good understanding. The fat-soluble vitamins, A, D, E, and K, are stored in body fat, and because of this, they can eventually reach toxic levels if too much of them are consumed. But having a possible stored level does mean that deficiencies of these vitamins, while possible, is less likely. On the other hand, excessive levels of water-soluble vitamins are not stored in significant amounts, and are mostly excreted as waste. This makes accruing toxic levels very unlikely, but it also means that these vitamins must be regularly replenished, or a vitamin deficiency may occur. Okay, really quickly now, here we go. Vitamin A in the form of beta-carotene, retinol, or retinol is needed for normal growth and development, adequate immune response to disease, and maintenance of epithelial cells and mucous membranes. Vitamin D can be created by sunlight on the skin or by eating several types of fish oils or from vitamin D fortified foods like milk, and is needed for calcium and phosphorus absorption and regulating calcium levels in blood and bones. Vitamin E can be acquired from various plants and plant oils and is needed to protect various cells from oxidative effects and hemolysis of red blood cells. Vitamin K may be best acquired from many leafy greens like kale and spinach and is needed for the formation of many factors necessary for blood clotting and for bone strength. Vitamin B1 or thiamine is best acquired from rice and pork meats and helps with carbohydrate metabolism and the proper nerve, muscle, and cardiac function. Vitamin B2 or riboflavin is best acquired from beef liver, milk, whole grain bread, and soybeans and is essential for nutrient metabolism. Vitamin B3 or niacin, best acquired from beef liver, chicken, tuna, whole wheat flour, and rice, is needed for energy metabolism and health of the skin and digestive system. Vitamin B6 or pyridoxine is best acquired from beef liver, turkey, or potatoes and is needed for nutrient metabolism and for cell membrane function and growth. Vitamin B12 or cobalamin is best acquired from clams, sardines, or beef and is needed for hemoglobin synthesis, general cell function, and energy and folic acid metabolism. Vitamin B9, most well known as folic acid, is best acquired from enriched cereals, rice, and lentils and is needed for red blood cell formation, functioning of the gastrointestinal tract, and protein and DNA metabolism. Vitamin B5 or pantothenic acid is best acquired from beef liver and mushrooms and is essential for fatty acid metabolism. Vitamin B8 or biotin is best acquired from liver, meats, milk, and is sometimes even produced by intestinal bacteria and is needed for many enzyme systems and nutrient metabolism and for healthy skin. And finally, vitamin C or ascorbic acid, best acquired from citrus fruits, red and green peppers, and broccoli, is a well-known antioxidant that is helpful to protect against infections and in wound healing and recovery, and is important for bones and teeth, cartilage, connective tissue, and blood vessels. Okay, so yeah, that just scratched the surface, so be sure to check your textbook for all the details. Let's move on to the minerals, the other well-known type of micronutrient. Nutritional minerals are defined as chemical elements that are essential nutrients for an organism to perform functions necessary for life. The main factor that separates them from the vitamins is the fact that they are individual elements, not organic compounds. However, if these elements were in their pure form, then they would range from insoluble to toxic to explosive, and I mean that literally. Those of you who've seen pure metallic sodium tossed into water, you know what I mean.
Oh, geez. fire,
go.
and then it explodes.
Yeah!
Okay.
Most of the minerals that we need we acquire in the form of not-so-volatile compounds, such as sodium chloride, table salt, and calcium phosphate from cow's milk. After ingestion, our bodies metabolize them into whatever form is most useful. There are 5 major minerals: calcium, phosphorus, potassium, sodium, and magnesium. These are considered major because they are present in the human body in quantities greater than 5 grams. All other minerals are considered trace minerals, present in smaller quantities, and depending upon who you ask or which book you read, there are at least 8 trace minerals with specific biochemical functions, and 12 or more others with general functions. Our textbook lists quite a few of them in some detail, and even though that previous vitamin marathon took less than 2 minutes, honest, go back and time it yourself, let's avoid doing that again. Instead, let's just briefly go over the 5 major minerals, and you can check the textbook for details on all the others. Calcium is the major mineral constituent of the human body, and almost all of it is stored in the bones. Besides being an important structural material, it's also used for the passage of materials into and out of cells, parathyroid gland function, nervous system function, blood coagulation, and cardiac cell depolarization. Milk is one of the best sources of dietary calcium, but note that vitamin D is also required for proper calcium absorption. This is why many milk products and calcium supplements are fortified with vitamin D. Phosphorus is the second most abundant mineral in the human body, and mostly found with calcium in the bones. Good sources of it are fish, turkey, milk, soybeans, baked beans, and lentils. With calcium, it helps build strong bones, but it also helps with energy metabolism, maintaining pH balance, and is needed within most cell nuclei. Potassium is commonly acquired from bananas, apricots, orange and tomato juice, and leafy greens. It's an electrolyte, and so it has a key role in fluid and acid-base balance, and it's needed for nerve impulse transmission, enzyme reactions, and promoting a regular heartbeat. Sodium is another electrolyte, and thus also vital in fluid and acid-base balance, blood pressure, and nerve impulse transmission. It is very easy to obtain plenty of it through the ingestion of sodium salts, and most people by far are at risk of taking too much as opposed to too little, unless they have specific issues with their electrolyte levels or retention. And finally, magnesium, which is the second most abundant intracellular cation. It plays a crucial role in several fundamental metabolic processes, such as DNA and protein synthesis, neuromuscular excitability, muscular contraction, energy metabolism, and bone stability. Significant dietary sources include wheat germ, fish, spinach, hazelnuts, almonds, and soybeans. And so, phytochemicals. As I said at the beginning, research into these compounds is ongoing, and so it's not clear yet whether they will be generally accepted as the 6th class of nutrients. Remember that this book was published in 2010, and now it's 2017, and still no decision has been made. Still, here's a little bit of info about them. Phytochemicals are defined as chemical compounds produced by plants through primary or secondary metabolism. Some compounds, such as lutein and lycopene, 2 common carotenoids, show favorable results when included in human diets. However, many of the several hundred other phytochemicals have shown mixed results, with some even resulting in adverse or toxic effects, though most by far simply show no significant effects at all. It is thus uncertain whether phytochemicals as a whole will be considered a nutrient category, or if the advantageous compounds will be included in a new category, or simply added to existing categories. And there you have it, our final diagram and the end of our presentation video on the fundamentals of nutrients and nutrition. Thank you for joining me, and I hope that this was helpful to all my classmates and to anybody else who may have watched it. And as always, feel free to like, share, subscribe, yada yada. If demand is great enough, and if I can somehow find more time outside of my studies, then I may do more videos like this in the future.